So the next transmission line protection scheme we are going to be going over is the line differential protection. So to implement this, you need identical relays at both ends, and you also need identical CTs at both ends. So this scheme basically facilitates the remote relay and the local relay to share their current values with each other. And once both the relays share their current values, each relay then calculates the operate current and the restraint current values locally. And in order to calculate the correct operate and restraint current values, the relay also checks for the channel synchronization, if the channel is synchronized or not. If the channel is not synchronized, then the um, the values which the relays share with each other, there's going to be a mismatch in those values, and that might lead to a misoperation. So channel synchronization is really important if you are using 87 or 87L or a line differential protection scheme. So this scheme operates only for the faults on the transmission line, and it restrains for faults outside of our transmission line. So in this example, I'll be using SEL 411L relay, and we are also going to be going over a few considerations while setting up the SEL 411L relay. So the first one is the CT saturation condition, external fault detection condition, channel asymmetry, and charging current condition. So this kind of scheme also requires a source of time. The source of time can be uh, taken from a channel-based approach or a time-based approach. So for the time-based approach, you need a GPS clock at each of the terminals of the transmission line, and the channel-based approach uses a ping pong method which calculates the delay in the channel. So in this, we are going to talk about how the relay identifies a fault. So the CL411L relay uses alpha plane characteristic. So the alpha plane characteristic calculates a vector, a vector value. This is a ratio of the current seen by the local terminal relay and the remote terminal relay. And each relay also calculates, as we discussed earlier, each relay also calculates operate and restraint current magnitudes locally. Based on these values, relay determines if the fault is in the zone or out of zone, or in other words, if the fault is on the transmission line or out of the transmission line. So initially, we can consider a normal condition. So in this normal condition, the current going into the relay is equal to the current going out or flowing out of the relay. So if you refer to the calculations part of the slide, the operate current is equal to 0 as IR is equal to negative or IL is equal to the negative of IR. They are both in phase opposition, so they cancel each other out, and the operate current, or the current flowing through the operate coil of the relay, is zero. So for the same example, if you were to plot the k vector on the alpha plane, this is how it's going to look like. So you have IL, which is ISEC in this case, and I have taken it and have assumed IS at an angle 0. And similarly, IR, the magnitude is going to be the same, ISEC, but it's going to be in phase opposition. So it's the angle of that current is going to be 180 degrees. And if we solve for that, for those two vectors, we divide those two vectors, we get -1 on the alpha plane. So that's the base point of our alpha plane characteristic. So relay tries to be at that -1 restraint point in the healthy condition. So now let us consider an in-zone fault condition. So there is a fault on the transmission line. Now, if you observe the direction of the currents on the primary and the secondary um, of the transmission line and on the secondary of the CT as reversed. So, so the current flowing into the relay is no longer equal to the current flowing out of the relay. For simplicity, or for the sake of this example, I have considered the current in local terminal relay as 3 at an angle 80 amps, and at the remote as 2 at an angle 70 amps. So by using those equations for calculating I operate or operate current and restraint current, we get 5 amps for both. So a couple things to keep in mind over here are, while assuming while I assume the values of the angles in this example, the angles of the current will be dependent on the source impedance and the X by R ratio of the circuit. So once you do a fault analysis, um, the result of that fault analysis will give you those angles. And as you see, the I operate current value is 5 amps. And if that I operate value is greater than the pickup value, the pickup current value of the 87 element, then the relay will operate. Now for the same example, if we were to plot a vector k on the alpha plane by dividing the current vectors, we get 1.5 amp at an angle 10 as the k vector. And normally all the faults which are on the line will lie in the red area shown on the alpha plane. So now talking about the external fault detection and CT saturation condition. So for an external fault, CT saturation will not compromise 87L protection scheme when you're using a SEL 411L relay. So as the CT saturates, the restraint current increases and the operate current remains the same. So one thing to keep in mind over here is we're talking about an external fault, which is not on the transmission line. So keeping that in mind, if the CT saturates, the restraint current increases as it's the sum of the magnitudes of both the currents, and the operate current remains the same as it's the vector sum, the magnitude of the vector sum of both the currents. So they will cancel each other out. So once the relay detects a rapid rise in restraint current and no rise in the operate current, it identifies this condition as an external fault condition. And if this happens, if this condition is satisfied, then the relay anticipates that the CT has saturated or is going to saturate. It restrains from operation and allows the fault to be cleared locally wherever the fault has occurred. So now how does the alpha plane characteristic look like once you take into consideration the local saturation and the remote saturation? So depending on which CT saturates, the vector K moves left if if the local CT saturates, and it will move to the right if the remote CT saturates. As so it will move for a local CT saturation condition, it will move left as the real part of the vector K is going to be increasing, as it's the local current vector is in the numerator part of the vector K formula. So as the numerator increases, the real part will also increase. And as far as the remote CT saturation condition is concerned, the current vector in the formula for vector K is in the denominator. So as the denominator increases, the value of vector K is going to be decreased, and it's going to fall below its -1, the ideal restraint point, and it's going to move rightwards. So other thing which the SCL411L relay takes care of is the channel asymmetry. So this occurs when the transmit and receive signal takes a different route to the remote terminal. So from this figure, you can see the cross indicates um, a broken link of a transmit signal between multiplexer A and multiplexer 4. So if the transmit of multiplexer A is broken, it's going to take the longer path through multiplexer 2 and multiplexer 3 and eventually to multiplexer 4. So now in this condition, the multiplexer A receives a signal from multiplexer 4 on a different path and sends a signal to multiplexer 4 on a different path. So that causes channel asymmetry. So once the relay so once the relay determines that there is a channel asymmetry, then it usually switches on to a different channel, and the relay tries to use the same path to its destination relay, which is multiplexer 4. So it's going to switch off the shorter receive path, and it's going to take the longer path for both receive and transmit signal. If this is not done, there will be an asymmetry between the local current and remote current. So digging a little deeper on channel asymmetry, let's say there is a propagation delay due to due to unevenly long transmit and receive paths. Let's say that delay is about 10 milliseconds. And propagation delay is basically calculated by using a ping pong method. So let's consider a local terminal relay. It sends its current magnitude to the remote terminal relay at a certain time. And as soon as it sends a packet of data to the remote terminal, it logs the time at which it sent the packet of data. And now it waits for the remote terminal to respond to that packet of data. So as soon as the local terminal relay receives a handshake signal from its remote terminal, it logs that time. So that's what it's called propagation delay. So if you divide that propagation delay by 2, it will correspond to the channel asymmetry. So over here in North America, it's they use 60 hertz of AC frequency signal or power. So 60 hertz corresponds to 16.67 milliseconds of of a one single wave. And that and on that 60 hertz signal, 5 milliseconds corresponds to about 110 degrees of current misalignment. So ideally, if you see the waveform below, both of those waveform should be superimposed together. There shouldn't be any phase difference between them. But in this case, because of different paths taken by the transmit and receive signal of the multiplexer, the local terminal current doesn't match with the remote terminal current, and they are mismatched by about 110 degrees. So to take this into account, 411L relay moves its restraint curve. So to incorporate this current misalignment, we extend the restraint region by 110 degrees. So on this diagram, you can see the restraint region is shown in the blue circle. So on top of that, we could also have high resistant faults. So the fault current is usually limited by the fault resistance. On a usual fault, we don't have much fault resistance, but in case we have high fault resistance or a case of high fault resistance, just to cover all the cases, we have to move our restraint curve or define a restraint curve. So in case of a high resistant fault, high resistance fault, the load flow continues. It doesn't stop. So our local and remote relay will see current in both in forward direction. So there won't be any. So there will be very less um, operate or differential current flowing through the differential relay. So in this case, the relay will see that fault um, on your left. If you see the diagram below, on your left, you have a red operate region. So that's the region which is denoted by the um, high fault resistance fault. And as you can see, it clearly lies outside of the operate, or lies outside the restraint zone, and relay will trip if it sees a high resistance fault. So there's one last condition which we should take into consideration is the charging current condition of the transmission line. So the relay compensates for the line charging current by estimating an instantaneous of the total line charging current on a per phase basis, and it subtracts this value from the measured differential current. So to calculate the impedance, the relay also, or not calculate to calculate the fault current, or to calculate the charging current, it also needs a susceptance value. So this susceptance value is provided by the user, and it also uses the line voltage value in order to calculate the line charging current in real time. After this condition is met, the or by this condition I mean, if the line charging current value which is calculated is above the measured is below the measured value, then the relay declares that this is a line charging current condition, and the relay should not operate on a differential uh, pickup. I think that's all I had for today, and I took all this information from the relay testing handbook and the instruction manual of the SCL 411L relay. Thank you so much. If you have any questions, you can go ahead now.
Now I am unmuting, so you can unmute yourself and can ask the queries. Now unmuting option is enabled, so you can unmute and ask the queries.
Hello.
Yes, go ahead.
Hello. For this line differential scheme, is there a restrictions on the line length, or how much length of the line should be for using this line differential protection?
I would say the only limitation um, is imposed by the length of the fiber optic cable which we can have. So if we have a direct fiber, a single mode direct fiber over um, the wavelength of 1500 nanometers, then we can have a 120-kilometer long line, a point to point. But usually it's used for a shorter line, about 80 kilometers or 50 kilometers. That's what I have seen.
Hmm. Okay.
Hope this answers your question.
Yeah. Yeah. One more question is there. For the initial slides about that wave trap and the um, series resonance filter.
Yes.
Mostly in MSCTCL, I have seen the web trap used, but what is the application of the series resonance filter then?
Series resonance filter. um, so the line trap. So I'll just do a comparison between line trap and the series resonant filter. So line trap is a parallel resonant filter. It blocks. So we are talking about talking in terms of carrier frequency, right?
Yeah.
So the line trap or the parallel resonant filter is tuned to the carrier frequency. So once you tune that filter to carrier frequency, it acts as an open circuit. So it doesn't allow the carrier frequency to go into our substation, and it just restricts that carrier frequency to the protection line. But we need our local terminal relay or a remote terminal relay to get that carrier frequency, right?
Hmm.
To receive that carrier frequency. So in order to receive that carrier frequency, we need to filter out the carrier frequency from our power transmission frequency, which is 50 hertz. So you need something which offers really low resistance or impedance to a carrier frequency and offers a really high impedance to a power frequency. So the
Yes.
series resonant filter acts as a really low or a short circuit, or it filters out a carrier frequency from the transmission line. And once you filter out a carrier frequency, you can use that to send or receive signal between the transmission line and not worry about having the 50 hertz signal coming to your relay. So you're restricting the power flow to your relay. Um, the 50 hertz power flow, you're just dealing with the carrier frequency.
Okay. Got it. Got it.
Any other queries to other participants they can ask? Otherwise, we can conclude the session. I think no one has further queries. So now I would like to conclude the session. So thanks to Saurabh for this wonderful session and very deep knowledge about the transmission line protection. As well as I am thankful to all participants for joining this session. And I observed one thing that most of participants have registered, but they have not actually joined the session. So that thing also we have to be very focused about it. So once again, thanks to all of you. Especially thanks to Saurabh for this one very good session for us.
And thank you everyone for attending this session. It was a pleasure.
Thank you.
Thank you very much, sir.